Okay, here's where we left off. What we did is we plotted critical stress, Euler's critical stress versus slenderness ratio, and we found out that the critical stress goes way down as the slenderness ratio goes up. So let's talk about effective length. Okay, so Euler's formula assumes an ideal column with pin joints at the ends. The pin joints allow the column to rotate at the ends. Now, if we had different column end conditions, like say a fixed end, that would affect the buckling points of inflection and hence the critical stress. So how do we deal with ends different than pin joints? We use an effective length factor, a factor K that's applied to the Euler's formula. So we use the same Euler's formula, except we apply a factor to it. Okay, so here are the effect of end conditions. Here is the Euler's column. It's got a pin joint at both ends. We're free to rotate the column at the end. Our effective length is 1. Okay, when we have a fixed at both ends, our effective length goes down to half of our length. Okay, and then if we're fixed at one end and pinned at the other, our effective length is 7/10. Okay, and then if we have like a flagpole, it's fixed at one end and then it's free at the other end, our effective length is actually 2. So when you're using effective lengths and effective length factors, I want you to use table 18.1, and when we're doing our problems, always select recommended K values for design and analysis. Pull this one out. So if you have a problem where you're using a fixed pinned type of an arrangement on your column, you're going to use 0.8 for your K factor. And how does this get applied? Equation 8.3 and 8.4. So equation 8.3, we put K times L. We put that right here in the slenderness ratio part. So your slenderness ratio right here. We put the K in the slenderness ratio. That's where we do it. We're really, again, we're not going to use equation 18.3 too much. We're going to use 18.4 to find the critical stresses and then multiply that by the column area to get the critical loads. So then we're going to talk about example 18.3. Let's talk about real columns. Okay, so what we have here is we have this zone, a band of lab results. So the lab got together and they made a bunch of different columns with different slenderness ratios, and they subjected them to loads and see where they would fail. Okay, so we have this band of experimental test data. As you can see, down in this higher slenderness ratio range, we have our Euler's curve does fairly well predict the failure of these columns due to buckling. But you get to a certain point right around in here somewhere where, you know, the Euler's curve doesn't quite follow the experimental data. And then over here, when your column gets really short, like we discussed before, you have your yield strength becomes the limiting factor. Okay, so for short columns, small KL over R, you have failure due to yielding. Okay, at longer columns, KL over R, you have failure due to buckling. And then in here, we have these lab results here that we're going to have to try to deal with. So this graph shows that the Euler formula predicts elastic buckling up to a certain slenderness ratio, and that normal compressive failure occurs at yield stress levels, and those are at lower slenderness ratios. This graph is fairly interesting. It's just presenting a practical method of determining what a design criterion is. And essentially what they've done here is they said, well, you know, in my design, so this essentially would be a design criterion. Okay, so here at the low slenderness ratio, we actually have a factor of safety of 2 because our yield strength is 50 KSI, but we're only allowing our stress to go to 25 KSI. So that's a factor of safety of 2. And in this case, we're limiting this one here. We don't want to go over 150 slenderness ratio. KLR over R is 150. We get over that, we got an unstable column. So this could be a design criterion. And so what we're going to do is we're going to talk about 3 methods of design criterions for these columns. And one is the AISC, axially loaded structural steel columns. So their acceptance criterion looks something like this. Say if the factor of safety to yield was 1.67, so our yield strength is 50 KSI, but we're only allowing it to go to 30 here at the low slenderness ratios. And then we have what we call a critical or a transitional slenderness ratio, because we have one curve at the top and then one curve at the other part. So here is how the methodology works for the AISC. First of all, you calculate a critical or a transitional slenderness ratio. Okay, so that is 4.71 times the square root of the modulus of elasticity divided by the yield strength. And then if your actual KL over R is greater than the transitional KL over R, you apply one factor because your failure mode is most likely buckling. But if KL over R is less than or equal to the transitional slenderness ratio, you apply a different formula. And that's going to account for material failures as well. Okay, so that would be one method. And then I present another method too for axial loaded machine parts. It's a very similar process, but some of the equations are slightly different. If the column is slender, if KL over R, and this is your transitional KL over R, and then it's intermediate if that, and then you apply the proper equation. Okay, so I'm giving you 3 things to do, and those are covered in the examples. We're going to do the AISC. It has one method, this method here. We're going to also talk about the axial loaded machine parts. It has another method. And then we're also going to talk about timber beams. And then that'll be covered in the examples. So please refer to your problem examples for Chapter 8. Thank you.